So while the others are joining, so I will just start first. Okay. You see here, okay, based on yesterday's lecture, okay, so we will actually try to recall the important concepts that I taught you yesterday. Okay, so the further aspects of equilibrium, okay, where we are going to learn about certain formulas. Okay, so we will start off. Okay, the formulas, there are three formulas, the main important formulas, but I put it over here, everything. Okay, so we will start off, okay, with the KW. So what is KW? KW is known as ionic product of water. Okay, so something like equilibrium constant, yeah, ionic product of water. So basically, how do we get this particular formula? So basically, we have H2O. Okay, they are going to give you H plus and then OH minus. Okay, so what happens over here is, okay, we know that, okay, if I want to write the KW or the KC, I will write it down as H plus, okay, concentration of OH minus divided by concentration of water. But this concentration of water is constant. Now, because this concentration is constant, okay, we are just going to take it as concentration of H plus times the concentration of OH minus. But always remember, okay, when we have, okay, the equation, when you have a partial dissociation of anything, okay, we know that the number of moles of this H plus and the number of moles of OH minus must be the same. It's 1 to 1, okay, the ratio 1 to 1. So this is going to be, you can simplify by saying that, okay, the H plus is the same as OH minus, the concentration. So I can simplify, okay, by writing it as H plus times OH minus, you change it into H plus, and you will have this formula, okay, to the power of 2. Okay, so this is simplification. Why we change it into this? Because it is going to help us to calculate the pH of pure water. Yeah, the pH of pure water at 298 Kelvin can be calculated using this formula. That's the reason why we have to use this formula. Okay, because, okay, generally, if you want to keep it as this formula, still okay, okay, still okay. But if you want to calculate the pH of water, then we have to use this formula, which is going to be pH equals to negative log concentration of H plus. So when I delivered the lecture yesterday, yeah, maybe it's my mistake because I thought, okay, in IGCSE, you have already learned about the formula to calculate pH. So now I know, yeah, Jackson mentioned, yeah, we didn't know. Okay, fine. So now you just memorize this formula, yeah, which is going to be negative log concentration. And if you study in your maths, okay, generally we use log. I think you just use the log to calculate only. But I want you to understand why we introduce log. Okay, when you have a number, for example, 0.0011, for example. So maybe I make it simple like this, 0.001. And if I want to draw a graph, okay, there is going to be a lot of decimals. And if I want to change, it's 1 times 10 to the power negative 3. Okay, just they don't want to write it in that form. They want something in a whole number. So what they have included, yeah, let's use log. Log is going to convert, okay, the small numbers into something that is going to be nicer to see. That's the meaning. And then why there is going to be negative is included. Negative is included because simple reason. If I want to make convert this number into something a nice number, okay, I can use negative log. Negative log 1 times 10 negative 3. Okay, negative and negative will become positive. Log 10, 10 to the power of 10. So this is going to be 3. So I have a very good number, which is 3. Okay, so the purpose of log is to change these small numbers into a very nice number. That's the meaning. Okay, and why we do that? Okay, when they plot the graph, yeah, it's going to be much more presentable. Okay, so that's the reason. So it must be negative. If you don't use negative, then this value is going to be negative. So that's the conversion and why we use the log over there. Okay, so that is the reason why you use log. If you don't want to use log, also fine. Okay, but the meaning is still the same. Okay, the meaning, what does the log represent? Okay, what does pH represent? If you have lower pH, it means that the concentration of H plus is high. Okay, something like your Ka. If your Ka is more, pKa will be less. Okay, something like that. So the value, okay, if you have pH 1, you are comparing with pH 5. pH 1 is a stronger acid. Okay, why it is a stronger acid? Because it has more concentration of H plus. That is the meaning. So you need to know why we do that. Okay, but now coming back to this part, why we have to change this? Because if I want to calculate the pH of pure water, okay, because they know Kw, the ionic product of water, is always 1 times 10 negative 14. This is going to apply, okay, for pure water at 298 Kelvin. And when you do that, okay, if I want to find the concentration of H plus, you can just use the formula square root, and you will have concentration of H plus of pure water is going to be 1 times 10 negative 7. You can calculate using the formula pH negative log concentration of H plus, and the pH of pure water is going to be 7. Yeah, Jeffrey can. So pH is going to be 7 at 298. This is going to be information that it will give us. Yeah, and we have learned about this pH. If you are talking about water, okay, if you're talking about water, most of the time when we want to calculate the pH of this sodium hydroxide, potassium hydroxide, we are using that formula, which is going to be Kw. Okay, Kw equals to H plus, okay, and then OH minus. Okay, this is when you are calculating pH of something where you don't have the H plus directly. So if, like, say, for example, I want to find out the pH of sodium hydroxide, okay, and they give you what is the concentration, for example, let's say 0.01 mole per dm cube. So what we do over here is, okay, we have to use this formula. Kw equals to this. What is the assumption? Basically, why we are using Kw? Why water? Because water, okay, if you have water, you are going to add sodium hydroxide in it. And when you have water, water itself, okay, will give you H plus and OH minus. If you add sodium hydroxide, it means there's a increase in concentration of OH minus. And we know when we learn about LCP, yeah, when the concentration of OH minus will increase, yeah, the position of the equilibrium will be shifted to the left. Okay, but what we have learned also is, okay, when you add sodium hydroxide, it means you increase the concentration of something. Your Kw or your Kc, they don't change. Okay, it remains constant. Kw or Kc will change only when you increase the temperature or you decrease the temperature. So that's why, okay, we are going to use as this is the base, like not base, this is going to be the main concept, the main subject, okay, as our calculation. Because the Kw remains the same, you can just use H plus times OH minus. You can ask me why you don't use the concentration of H plus times the concentration of H plus. The answer is quite simple. This is not pure water. You have pure water and then you are adding sodium hydroxide. Now it's a solution. So if it is solution, your concentration of OH minus is not the same as concentration of H plus. So what we put over here is whatever concentration of OH minus that we have, we put over there. But what is our assumption? The assumption is we are going to assume the OH minus from water is non-existent. That is going to be the assumption. Okay. So when I put this, I'll just put, yeah, I want to find out the H plus. Okay. How do I find out concentration of OH minus? I know sodium hydroxide gives me Na plus and OH minus. 1 mole, 1 mole, 1 mole. So if I have 0.01, so I will have 0.01 over here also. So here I put 0.01. And then the Kw don't change. Okay, I put over here. And I can calculate what is my H plus, okay, which is going to be 1 times 10 negative 14 divided by 1 times 10 negative 2, and I will get 1 times 10 negative 12. Okay. And I can calculate the pH. pH is negative log H plus. You put in and you will get the pH, which is going to be 12. So I've managed to calculate the pH of sodium hydroxide, something like that. Okay, that is the reason why, okay, we need to learn about this KW formula. Yeah, so don't think that KW is ionic product of water. It's only for pure water. No, we will use KW for all the situations. Yeah, for sodium hydroxide, potassium hydroxide, and so on. Now, if you look at these two formulas, okay, KW and pH and so on. Okay, we use them, okay, especially the KW formula. We use them when you are going to have strong base or you have strong acid. Okay, you are going to get, like, for example, ACl. Yeah, all the H plus you can calculate and then you can apply the pH formula. Sodium hydroxide, we know all of the OH minus is going to come over here. I can apply. It's going to be for strong base and strong acid. What if I have weak acid and weak base? Then you have to use a different formula. Okay, for your syllabus, you only learn about weak acid. You do not need to learn about weak base. So when we use, like, for example, Kc is equilibrium constant. So I use for pure water is going to be known as ionic product of water, which is going to be Kw. Okay, but now if I'm going to use it for weak acid, so I'm going to use Ka. Why? What is Ka? So basically, if you have an acid, okay, it's a weak acid. So generally, they will have this reversible equation. Okay, what does it tell me? Okay, only a certain portion of the Ha is partially ionized to give you H plus and A minus. It means that if you have 1 mole per dm cube, I cannot say for certain, okay, that this is going to be 1 and this is going to be 1. This is wrong. Yeah. But what I can say is, okay, I can say that the number of moles of this and this will be the same. Why? Because 1 to 1. Okay, that is what I can say. So here, okay, if I want to write down the Kc, okay, normally Kc, how do I write? I will write down like this. Okay, concentration of this divided by Ha. And normally we write it down when they are at equilibrium. Do remember there are few assumptions that is being made. Okay, the assumption is I'm taking, okay, the concentration of H plus directly from the weak acid. But I know acid can only behave as an acid when there is water. And I can write down water, okay, supposed to be something like this. I know that water also gives me H plus. Okay, but when I apply this formula, my assumption is I am going to ignore. I'm assuming that there is H plus from water is non-existent. Okay, H plus from water is ignored. That is going to be the first assumption. Okay, it means that this is not accurate. Okay, but we have to put that assumption. Now, second thing is, okay, we know at equilibrium means, let's say, for example, if I use the ice method, initial, change, and equilibrium. Okay, I know that if there is going to be a change, this is plus x, this is going to be plus x, this should be minus x. Let's say start with 1. So at equilibrium, it's supposed to be 1 minus x. Okay, but I am not going to use 1 minus x. I will just use 1. So it means that this Ha, I am going to use initial concentration of the acid. So another assumption that I am going to use is, I know that weak acid, they will dissociate partially. Okay, so at equilibrium, they're supposed to have less than what is the initial concentration. But our assumption is, I am going to assume, okay, there is going to be the concentration of Ha, okay, is going to be, we are going to use the initial concentration. So our assumption is, okay, we say that the dissociation or the amount of the acid that is ionized is too little. okay, until we ignore, okay, until we ignore what? We ignore the X. Okay, it means I'm going to use the initial concentration of the acid. So ignore, okay, the dissociation. So these are going to be the two main assumptions, okay, that we use this formula. Okay, and if we can proceed further, okay, and I told you, okay, that this is X, this is also X. I can simplify like something like for Kw, yeah, which is going to be the concentration of A minus, okay, is going to be the same as concentration of H plus. So I can simplify this, okay, because this is going to be acid dissociation constant, Ka. So I change Kc now is Ka. And what is Ka? What Ka tells us? Ka tells us that how much, okay, if Ka is more, it means this is more, this is more. It means that the dissociation is going to be more. So it means that if you have bigger Ka, okay, it means that it's going to be a better dissociation. It means that it is a weak acid that can dissociate more to give you H plus. Okay, so it's going to be a better weak acid. Okay, it's a better weak acid. So that is going to tell us that. Okay, but we can calculate the pH. Okay, the reason, okay, why we have to simplify this, because I want to calculate pH. So I know that H plus, okay, then this A minus must be H plus because it's the same, and then divided by concentration of HA initial, okay, and I will have the concentration of H plus to the power of 2 divided by concentration of HA. Now, this is going to be how we get this formula. And this formula is only valid, okay, for your weak acid. So you always use this formula for weak acid. You do not need to think about ice, okay, initial change, equilibrium, and so on. Straight away, if they ask you to calculate the pH, you can do that, okay, but you must know the Ka. Without knowing the Ka, you will not be able to calculate the pH of that weak acid. Okay, so you need to remember that. And then, of course, okay, we went through, okay, if you have the pH equals to negative log concentration of H plus, you can also use the same thing, pKa. Again, if you have a value which is going to be 0.001 or something like that, you want it to look nice, okay, to look presentable. So you can always use the negative log, okay, but what we are going to get from that value is important. I know that if your Ka is going to be bigger, okay, it means it's a better weak acid. So it means the dissociation is more, okay. So I will say better weak acid. Dissociation is more, okay. But I know, okay, like for example, similar to pH, if you have lower pH, it means that it is going to be a very strong acid. If it is going to be higher pH, like for example 5.5 and so on, then it's a weaker acid. Similar concept, okay, if you have a better weak acid, the better weak acid will have something like pH. The pKa is going to be lower, something like pH. Okay, a smaller pKa. A smaller pKa will indicate that your Ka is large. Okay, and this will help us to identify between two weak acid, which one, okay, will be a better weak acid. Now, if there is a question, do we have Ka, okay, for HCl? The answer is no, we don't have. Okay, what is Ka? Acid dissociation constant. And acid dissociation constant is only being used, okay, to tell how much, okay, the acid can dissociate. When it comes to strong acids like HCl, HNO3, you no need to think about that, how much it's going to dissociate. The answer is it's going to be completely dissociated. So you will not have Ka when we are dealing with strong acid. So we will only have Ka, okay, or we will only use this formula, okay, whenever we are dealing with weak acids. This is very, very important. Yeah, very, very important. So if you look at it overall, okay, the first half of the lesson, I think when you look at it, maybe the first 30 minutes or 45 minutes of the lesson was only discussing about this, okay? Only discussing about how to do the calculation using KW, how to do the calculation for this, how to do the calculation for this, and so on, and what is going to be the assumption. So this is done. Yeah. Now I will move on to the pH graph. Yeah, I know I went very fast yesterday. Yeah, but it's okay. Okay, it is understandable. We cannot go directly to lecture. Yeah, when we haven't learned something. Yeah, that is actually it's okay. Okay, but you will understand more today. Okay, when I go through this. Yeah, because you have already I already started this with you guys. Yeah, so you see pH graph. Okay, you can use the pH graph, okay, to show what will happen to the pH when you mix acid and base. And do remember, acid and base, yeah, acid and alkali, they are going to undergo neutralization, and there is going to be pH will be changed. And in this case, okay, you can see that in this graph in your syllabus, they are using, okay, they are measuring the pH of the base. Okay, they're measuring the pH of the base, and they are keep on adding the HCl. It means, what do we expect? We will expect the pH from something that is bigger, something that is higher, and it's going to slowly change into acid. Yeah, so acid. So even I think this one, not all the time I'm going to use HCl. Like for example, strong acid and strong base. Let's say I give you one example. I'm using HCl and then NaOH. Yeah, and then the volume of HCl. Okay, so what will happen? Okay, you can see here, okay, I am going to use strong base, and I'm going to measure from strong base. Strong base, the pH will be roughly at 13. Yeah, you can memorize that. Okay, the pH is going to be roughly at 13. And what will happen? Okay, the pH, as the acid is being added, the pH is going to drop, something like that. Okay, as they keep on adding. And what will happen? Okay, at certain point, the pH will have a sharp fall, and that sharp fall is going to happen at this particular range, 11 to 3.5. You can memorize this. I think in the previous lesson, even in the textbook, they have used 10.5. It's okay. We can use 11. No problem. Easier to memorize. So 11. So roughly, let's say this is 11. And then up to 3.5, somewhere here, 3.5. Okay. What will happen? There is going to be a sudden drop. Okay, there's going to be a sudden drop. Okay, it shouldn't be straight like this, sudden drop. Okay, and then, okay, do remember it's a strong acid. Okay, it's a strong acid. Strong acid means the pH, okay, if you keep on adding, the pH will go on until maybe it's reaching 1 or something like that. Okay, now what we can do over here, based on this sharp fall, okay, if you look at the midpoint of this is going to be what we call as equivalence point. And what is equivalence point? The equivalence point is going to tell us that this is going to be, let's say for example, the equivalence point for strong acid and strong base is going to be at 7. And you can say that, okay, at this particular volume, okay, of this HCl, this is going to be, let's say, for example, 20 cm cube, for example. 20 cm cube, okay, is going to be the exact amount of the acid required to completely react with the OH minus from sodium hydroxide. That is the meaning. Okay, so that is what we call as equivalence point. So the equivalence point for strong acid and strong base, you memorize, is 7. Okay, it's 7. And the same thing will apply for the equivalence point for the weak acid and weak base. Okay, so I'll just put 7 over here. Okay, but there is no sharp fall whenever we are dealing with weak acid and weak base. Yeah, and I will just go through here. Okay, you see weak acid, weak base. Okay, example. Okay, maybe I'll give you example. Ethanoic acid is a weak acid. Okay, and then weak base is ammonia. Okay, and here I cannot use volume of HCl anymore because I'm going to use weak acid, right? So it's volume of CH3COOH. And you do remember just now I started with 13. Okay, it's a strong base. But now you see, ammonia is a weak base. You start with 11. Okay, it's a weak base. Okay, you start at 11. And of course, they are going to drop. Okay, but we need to know where or what is going to be the sudden drop. Okay, the answer is there is no sudden drop. Okay, there is no sudden drop. So they will just come over here, maybe something like this. Then they go on, and then they will decrease. Okay, but do remember, if you keep on adding this acid, they are not going to go at pH 1 because this is the weak acid. So they will just go maybe around this 4 or something like this. Okay, somewhere there. Okay, so this is going to be the graph, okay, for weak acid and weak base. Yeah, so the sharp fall, there's none. Okay, so if you use this concept, okay, if I want to sketch the graph, let's say I'm dealing with strong acid, so HCl, okay, with a weak base, maybe ammonia. Okay, do remember I'm measuring the pH, okay, from the base itself. So you see the weak base, okay, I'm not going to start with 13. I'm going to start with 11 because why? Ammonia is a weak base. So I'm supposed to go down, okay, but I do not know where is going to be the sharp fall. Yeah, this one, the sharp fall will come from, okay, 7.5 to 3.5. How do I know this? Okay, you just need to memorize. If it is going to be 11 to 3.5, okay, whenever you're dealing with strong acid, weak base, okay, just remember like this. If you have 11 all the way to 3.5, if you are dealing with strong acid, okay, it means strong acid will be more towards 3.5. So just take something from the middle of 11 to 3.5. What is the middle of 11? The middle of 11 is going to be somewhere at 7. Yeah. So that's why the sharp fall will happen at 7.5 to 3.5. So where it will go, so somewhere here, okay, somewhere here, there will be sudden drop, okay, all the way to 3.5 around here. Then there is going to be, they will continue to go until 1. Okay, why? You can see it's a strong acid. Okay, so the graph will look like this. So is my equivalence point still going to be 7? No, okay, because they are not at the middle. Okay, so what happened to the middle? It will go down a bit, okay, from 7 to become 5. Okay, how to remember this? Strong acid, weak base, strong will win. Yeah, so acid, the pH is going to be at 5. So that is going to be the equivalence point. What does it mean? It means that at this particular volume, okay, the H plus, okay, all the H plus has been completely reacted with the OH minus, something like that. So the equivalence point, okay, for the strong acid and weak base is going to be 5. It will follow strong. A similar method, okay, if it is strong base and weak acid, okay, you can see here, okay, the sharp fall. Remember just now, I told you from 11 all the way to 3.5. Now it's strong base and weak acid. So strong base means more towards 11. So take half of it from somewhere here to here. So somewhere 7 to 11. Okay. So the equivalence point is going to be the sharp fall. Okay. Will be 11 to 7.5. Okay. The drop. So if I want to sketch the graph, you see it's a strong base. If it is strong base, you start with 13 and it's supposed to go down. And then what is the sharp fall? I told you it will be from 11 to 7, something like that. So you see 7.5. So maybe at 11, okay, sharp fall all the way to 7. And then they come over here. Okay. And then it's a weak acid. They will not go all the way down to 1. Okay, so if you keep on adding, they will just come until maybe until 4, something like that. Yeah. So here, okay, earlier, okay, we know the equivalence point, strong acid and strong base. The equivalence point is 7. But now, because strong base and weak acid, strong base wins. Yeah. So it's going to be the equivalence point is going to be at here, which is going to be at 9. Okay, so it means that, okay, it just simply tells us that at this particular concentrate, at this particular volume, yeah, all the H plus, okay, has been already reacted with the OH minus. Okay, that's the meaning. Yeah, that's the meaning. So you have the equivalence point now. Strong base and weak acid, strong base wins. So it's going to be 9. Okay. So this is how you get this graphs, how you sketch the graph. And okay, and we have learned about how to use okay the indicator. Now, the indicator that I selected over here, I took 3 indicators. Let's see whether which indicator is suitable or not. You see, yeah, bromothymol blue, yeah, the pH range is 6 to 7.6. Yeah, so Audrey, can you tell me, can we use bromothymol blue? 6 to 7.6. 6 is here, 7.6 is over here. Can we use? As long, okay, I'll give you a clue over here. As long the indicator range is within the sharp drop, okay, you can use that. Yeah, you can use that. So Audrey, can you use that?
Yeah.
Yeah, can. Now, phenolphthalein. Yeah, Jackson, can you use phenolphthalein for this case? 8.2 all the way to 10, maybe somewhere here. Can we use?
Yeah.
Yes. Do remember, okay, your indicator is not a very accurate representation of equivalence point, but it will just show you the color change. So you do not need to make sure that your equivalence point must be in between of the indicator. No need. No need. As long that they are within the sharp fall, it's possible. So you see from 8.2, maybe somewhere here to 10, we see that the equivalence point 7 is lower than that. It's okay. Okay, it doesn't matter. Okay, you can still okay measure or show us the color change. So possible to use phenolphthalein. Methyl rate 4.2 to 6.3. Okay, to save time, I'll just put over here 4.2 to 6.3 within the range. Yes, you can use that. Yeah, so you can see all these 3 you can use, and we have a lot of other indicators as well. Okay, but now let's actually look at these indicators, okay, for strong acid and weak base. 6 to 7.6, okay, so 6 is somewhere here, okay, 7.6 is somewhere here, okay. So you see 6 to 7.6, okay, is it a good indicator to be used? If you ask me, okay, because the sharp drop is 7.5 only, okay, so still, okay, it still falls within the range. A small part over here, still possible, okay, but not a very good indicator. Okay, not a very good indicator. But if I have 8.2 to 10, you see, this is 8 all the way to 10. They are not at the sharp drop. Okay, so you can never use phenolphthalein for this case. Okay, you will not see color change. And then for 4.2 to 6.3, okay, 4.2 maybe from here to here, 6.3, yeah, you can use. Okay, this is how you identify. And then here, okay, if you use bromothymol blue, 6 to 7.6, 6 maybe somewhere here, 7.6, still possible, but not really good one. Okay, still possible, not really a good one. Phenolphthalein 8.2 to 10. Okay, 8 will be somewhere here, 10 should be somewhere here within the range. Yeah, can use. 4.2 to 6.3, 4.2 to 6.3. They are not at the sharp drop. Okay, they are not at the sharp drop, so therefore cannot use. So this is how we select the indicators, okay, that we want to use. Cannot simply use any type of indicator. Yeah. So if you have the last one, you don't use any indicator, okay, because there is no sharp fall. Okay, there is no sharp fall. You can never get okay the endpoint. Okay, what is endpoint? So I'll just tell you what is endpoint and equivalence point. There are two main different. Two of those concepts are different. You know, endpoint is going to be to show whenever the volume that is being added. That is the point, okay, where the color change of the indicator is going to happen. Okay, so when you do your titration, sometimes some people do the titration. Maybe I additionally 1 drop or 3 drop extra or something. Is it fine? The answer is still fine because it's not accurate. Okay, because we are using indicator. Okay, it's not that accurate. But if you want to have an accurate value, yeah, then we have to use pH meter. Then we can actually get an accurate value of equivalence point. So it means end point is the point where there is a color change of the indicator. It's quite close to each other. Yeah, equivalence point and end point. Yeah, equivalence point is going to be the exact volume, okay, exact point where H plus and OH minus has been reacted. That is going to be different. And this is going to be indicator. Why indicator is preferred? Because indicator is faster. Even though it's not accurate, the accuracy is still fine. Okay, it's still fine. It's cheaper. Okay, if you are using pH meter, it's expensive. It's going to take a long time because you need to do calibration. Okay, every single time when we use. Okay, we never use pH meter in school. Okay, but if you want to find out more, you can just go through YouTube and so on. Yeah, that is what I wanted to teach you today. Yeah, so I'll stop my screen sharing.